Okay guys, now we are going to look to another parameter in the air compressor, which is called as the volumetric efficiency. So what is actually the volumetric efficiency show us? If you can observe our first case, right? This is our first case and this is our second case. You can please recap back. What is our first case? The first case is basically when our VC is equal to 0, and our second case basically is when VC is not equal to 0. Okay, so this is our second case. So if you can have right here, if you can observe the amount of air inducted into the compressor, for the first case, the amount of air inducted into the compressor is VA minus VD. And in this case, the VD is equal to 0. The VD is equal to 0. Meaning what? Meaning that what is being inducted into the compressor is VA. And we can see that the VA is in between or in the swept volume of from TDC right here to the TDC right here. And we know that the swept volume is from TDC to TDC. Sorry, this is our BDC. Okay, so this is equal to the swept volume, the VS, right? So the amount of air inducted into the first case, or the VC equal to 0, the VA is equal to VC, right? But in our second case, which is the VC is not equal to 0, we can see that the reduction of volume inducted into the compressor. So it's not VS, but in this case VA minus VD. So that's why we can write for the first case right here, the IG as state 1, we can write here, this is a P1 VS equal to the MRT1. Meanwhile, for the second case, the P or the IG as state 1 can be written as P1 VA minus VD equal to MRT1. So there is a reduction of this the inducted air into the compressor. Okay, so in order to look how much depreciate of this volume, so this will be put as the volumetric efficiency. Okay, and the definition of volumetric efficiency, the first definition is the mass of gas delivered divided by the mass of gas which will fill the swept volume at free air condition of pressure and temperature. So the first definition is in terms of mass. So if I can write the first definition, so for the first definition, this is volumetric efficiency is equal to the M divided by the M if the volume is at swept volume. Okay, so this is what being said right here, would fill the swept volume. Okay, the mass of gas delivered to the mass of gas which will fill the swept volume at free air condition. So this is at free air condition, meaning that this is at P, in this case is at P1 T1. For right now is P1 T1. Okay, and then if we look carefully, what is our M? For the first case, what is M? M is equal to PV. In this case, I'm looking at the case for VC is not equal to 0. Okay, so what is our M? M is equal to the PV. What is our V? Our V is VA minus VD divided by RT. And what is our case of our P and T right now? The case of T and P is 1 and 1. And then the MS is equal to, again, this is P1, right? So if you look at the definition again, against what? Against the swept volume. Okay, the M, if we assume that the V inducted in as the Vs. So in this case, the V should be as Vs divided by R T1. Okay, and then we use the first definition to get what is our volumetric efficiency. The volumetric efficiency is equal to M, which is P1 VA minus VD divided by RT1, and then divided by MS. So I put here as multiply. What is MS? This is our P1 VS, and then should be our RT1. So this is cancel off. P also cancel off. What is left right here is VA minus VD divided by VS. Okay, and for our case, the VA minus VD is also known as the V divided by Vs. What is V? V is the amount of air inducted into the compressor measured at P1 and T1. So by this definition, or by the proving from the M definition, M divided by MS, this will lead us to the second definition that we can also use for volumetric efficiency, whereby the second definition saying that the volumetric efficiency is equal to V divided by Vs. Okay guys, so that is our volumetric efficiency. So try to get what is the efficiency for the example 12.4. Yeah? So for your exercise, try to get the volumetric efficiency for our example 12.4. Okay guys, this is the volumetric efficiency.